And we're live. Welcome to Brain and Spine Group Live. I'm Dr. Rad. We're excited to get into the show today where we're going to be talking about a major scientific discovery, if you will, that was recently published in one of the top academic journals in the world about a new advance in spinal cord injury research. And so I'm going to be joined by my good friend and guest, Mike Rollo, who is an MD PhD student at Robert Wood Johnson in Rutgers, New Jersey. And, his formal training as both a scientist and to be soon in a couple of years, a physician. We're going to kind of tap into his training as a scientist to help break down what's really going on in this new piece of research. Because obviously it's a big headline. The question is it really a big headline, or, is this kind of more hype than it is impact? I don't know. We're going to get into that today. It's going to be an exciting show. We're glad you're with us. Go ahead, say hello to us in the comments, the chat, a wave, an emoji, whatever it takes. Just let us know you're here. If you have questions, drop them in the chat. We're happy to see them. And before we get into the show, just do me a favor. Go on over to our YouTube page. Our channel is right down below. Hit that like, the subscribe button so that you can get all the updates about our future videos. We've got tons of content coming. We have lots of new initiatives as a nonprofit organization coming in the new year, and we're really glad you're with us. So with that, let's get right into the show. I'm going to go ahead and bring Mike in. Mike, welcome to the show. How you doing this morning?
Hey guys, thanks Ryan for having me. I'm excited to talk about this. I would consider it a pretty impactful paper, and of course we'll get into some of the details on it. But I think it's at the very least exciting. Shows we're moving in a positive direction.
What is it? Well, look, you said it's an exciting paper, all right? And as a scientist, what would it mean to you in your career to publish a paper in Nature where this paper was published? Like, obviously, as scientists, I get it, right? I'm asking from more of an antagonistic perspective, for people out there who don't understand, like, what would it mean for your career as a scientist to publish a paper in Nature?
Oh yeah, I mean, Nature is one of the top academic publications. It's a huge task to be able to not only develop the work, but to get it through the peer review and have it accepted into a journal like Nature. They're only going to publish, highly impactful work. It also means that there is a fair amount of rigor that went into the work, and that's something that when you see a paper that is published in Nature, generally you can have some level of confidence that it went through probably multiple stages of revisions, multiple reviews. So it should be solid work. That's not to say that some work that gets into these high tier journals don't end up having some flaws that are discovered later on. But it's definitely a huge achievement to have a paper that is published in a journal like Nature.
It's a career altering in ways, like opens up new job opportunities, I anticipate, right? I mean, I'm not a scientist, but that's always been my understanding.
Yeah, I think, looking at it as a graduate student, if you were the graduate student that this was your first author, PhD thesis paper, it's going to open up a lot of doors in terms of where you can do your postdoctoral fellowship. And, from there, if you get a good postdoctoral fellowship, you have a higher chance of getting a good faculty position at a top tier institution. We could talk for days about the academic pipeline, and there are certainly flaws in it.
So you're telling me that there's a professional pipeline that has flaws in it? I'm shocked.
Right.
Yeah. I thought it was as simple as, go get your degree and you're going to have a great professional career.
Yeah, I mean, it's not brain surgery, but...
What's that?
It's not brain surgery, but
sure,
it's pretty close.
Yeah. Anyway, so the paper that we're talking about today, why don't I actually just go ahead and pull it up? I don't know if we're going to break any copyright rules with YouTube, but just to show everyone what we're talking about. So Nature, this is the journal that we've just been talking about for several minutes, that basically anything that makes it into this journal, at least at face value, can be somewhat believed to be like very important, very significant. It goes through a very rigorous process to even get in. And so because of that rigorous process, generally it has to be something important. So when you see a paper like this with a headline that says the neurons that restore walking after paralysis, it kind of makes you stop and think, at least as somebody, a neurotrauma enthusiast like me, it makes me stop and think, like, this got to be something important. What did you think when you first kind of saw I sent you the article a couple weeks ago. Like,
Yeah.
what were your thoughts as both a up and coming physician as well as a scientific researcher?
Yeah, it's certainly a flashy headline. The neurons that restore walking after paralysis. It grabbed my attention at the very least, and I think that's what they're trying to get at here. Really the meat of it is once you get into the abstract and then the main of the text, and you kind of explore what techniques they use to discover these neurons that restore walking after paralysis. And I think the scientist in me was excited to see that there was something to back up this kind of flashy headline. It's not like what we see in the popular media a lot of the times where you
exactly
get that clickbait.
You get that like Wall Street Journal article or New York Times, and you're like, oh my gosh, they solved paralysis. And then you read the article, you're like, they didn't do anything. That's a scientific discovery that was made 10 years ago that they're just writing a modern day article about.
Right.
No, but in general, right, this is a modern scientific. I mean, when we get into like the quality and the extent of the work that they did, I mean, this has got to be a decade's worth of scientific work, if not more. I mean, I feel like I don't know any of these authors. They're in, where are they located? I think they're in Sweden.
Yeah, I think there was I think there was some in Switzerland. Maybe it was definitely a mostly European cohort.
Yeah. Oh, bottom line is I don't know any of these people personally. Sometimes, how small medicine and science can be in the United States. Maybe you've met somebody at a conference or whatever the case. I've never heard of any of these people, but I assume at least probably the most senior author on this paper, which is a very prestigious position, is more probably less reflective of what you did boots on the ground as it is, more reflective of your leadership, vision, and guidance of the team and the project, but highly regarded as the most important position on the paper, which is the senior author, the last person listed as the author on the paper. It's probably, quarter of their career, if not more, made just collecting all the information needed to go into a headline like this.
Yeah, and we'll get into it. But the aspect of the clinical trial, we know that takes time, right, to organize a clinical trial, to go through the regulatory process. So that alone, was at least several years, if not a decade of work that went into getting it to that point.
All right, so let's get into it. Let's get into sort of walking through this article, because obviously flashy headline. Now we got to see, do they back it up? Does the rubber meet the road? So the first thing, basically, the interesting part I thought about this paper is that, we talk in a typical, scientific research sense. We generally want to translate things. We want to take them from, the lab, the bench, what we call the bench, right? Because the bench laboratory work, we want to take it to the bedside. So it's starting in the lab, making a scientific discovery, finding a way to translate that scientific discovery into something clinical that's actually effective for patients, and then doing clinical trials to sort of substantiate a whole slew of, things, and, that actually results in it becoming like a treatment available to patients. Right. That's the typical pipeline. So obviously that's not what happened in this paper. You want to kind of give a little bit of an overview of how they reverse engineered this process?
Yeah. So just like you said, we normally talk about that bench to bedside process, and that for a lot of people that go into these MD PhD programs is kind of the prototypical model is you want to be somebody that works in a lab and is doing some experiments in cells or tissues or in vertebrate organisms, and then over time you want to be able to bring that into more preclinical and then eventually clinical models. With modern science and medicine, it's hard to imagine one person, doing that. But you want to have the ability as a physician scientist to step back and say, okay, this is the translational pipeline that these studies normally follow. What a lot of people forget about is in the mantra of bench to bedside, there is this notion of going back from the bed to the bench, right? So, from seeing something in a patient to then bringing it and wanting to study it in more cellular and molecular detail. And that, really represents what this paper is describing. So, they saw a phenomenon that was happening in patients that were receiving a particular type of treatment that we'll talk about. And they wanted to understand what were the neuronal or cellular and molecular correlates that underlie that phenomenon. So it was really fascinating, and it's evidence of the rigor that went into the paper here, and that they didn't just do a trial and show that a certain clinical product or technique was effective. They then went back and tried to figure out in another organism how it was effective. So really a nice approach in doing that.
Yeah, so they start the paper by kind of describing the clinical the clinical trial, right? The stuff that clinically was happening in patients that led them to then ask some of their research questions that they worked backwards to go back to the lab. Why don't we just show I actually found an interesting little video. Did you have any videos from the paper that you wanted to show?
Yeah, I think when we start talking about what the technique is, I've got a video that was part of the paper that actually shows how the rehabilitation technique worked and the effectiveness in patients. So if you want to show your video first, and then we can dive into that.
Yeah, let's just look at some videos. I mean, honestly, we can sit here and talk about like, oh, they, did this clinical trial, but to literally just see a video and see like what they're doing, honestly it's a lot more interesting. Let me turn the video on and get into. Oh, let me make sure we have audio on for this. There we go. Okay, now we should have the audio on. Make sure it's not going to blast us. All right, let's play it. You guys can hear this audio okay? So this, actually, let me back it up and kind of explain rather than right in the opening. So right here, this is the battery pack or the control. Actually, the battery pack is probably physically implanted in the patient. That they have there is probably like a little computer interface that allows them to like turn the spinal cord stimulator on and off. And so what they're doing is, obviously the patient is wheelchair bound at baseline like typically, and they're just turning the battery pack on, and now you're about to see how this turning the program on for the spinal cord stimulator actually changes his ability to walk. So he's able to kind of use his upper body strength to get into a standing position, and then with structural support, the walker, he's now able to actually voluntarily move his legs with the spinal cord stimulator on. This is just a little animation of what it looks like. So this is actually a pretty accurate representation of what this little spinal cord stimulator looks like. It's obviously an animation of how it's done surgically, but it's not far off. I mean, I've done a handful of these surgeries in my limited training, and depending on every patient's a little bit different. Obviously younger patients that are less scar tissue and things like that, it's a lot easier to get this paddle into the epidural space without not having a lot of scar tissue to work around. I've seen a couple patients where we tried to put them in, they were like older patients, there was a lot of scar tissue. You basically ended up having to take a lot more. Let's back this up here. It would take a lot more of this like surrounding bone out when you've got a lot of scar tissue in there. But in a young patient with limited scar tissue, hopefully you can just make very small accessible openings and you kind of just slide it up under between the bone and the dura, and then the spinal cord is inside the dural sac. So it's not actually laying right on the spinal cord. It's like spinal cord, the covering of the spinal cord, the stimulator lies over the covering of the spinal cord, and then there's bone around all of that. And so that's kind of just basically you slip this paddle in, then you make another incision on the patient's back where you can make a little pocket and you stuff the battery pack that powers this this little stimulator probe. You stuff that into a little pouch made under their skin, and then you sew it all up. It heals, and then the battery pack connects to this little computer interface that you saw, and that's what allows you to control it from outside the patient's body. And so that's the gist of what epidural electrical stimulation is clinically. Just for people who aren't doctors, who've never seen this type of thing before, it gives you like a little bit of sense for like clinically what was happening, because the importance of that in this scientific discovery is that basically they were doing this clinically. They were doing these spinal cord stimulators clinically, and they were seeing that it was improving patients' ability to walk, but then they didn't understand exactly why, like what was happening that was improving patients' ability to walk. So it's sort of like they and so that's what Mike's referring to when he's talking about sort of reverse engineering from observing that clinical improvement.
Yeah, and Ryan, correct me if I'm wrong, but I mean, elements of this have been around for, at this point, I mean, decades, right? Where we've done spinal cord stimulation, even if it's not directly for spinal cord injury, but for like chronic pain or neuropathic pain.
Yeah. So actually, they comment in the paper that I think early iterations of the clinical trial, they had to take the stimulators that they were using, that were traditionally used for chronic pain patients, and adapt them for use in these patients.
Yeah. So that's an interesting note. This isn't, at least theoretically or even in practice, a particularly new thing. Even if it's being used in a new way. So that's what's really unique.
It's sort of repurposing of known technology that's obviously used and discovered in another clinical condition.
Right, exactly. And that's pretty common in medicine. I think we see, whether it's pharmacologic agents or
drugs is what he means by pharmacologic agent, right? Yeah. Drugs used for one thing, and then they find out they're like, hey, it actually works for this other thing, and then that's how you all kinds of stuff. I mean, even like it's actually much more common, I think, than you probably understand in medical school.
Yeah.
At least that was my experience. I feel like I got out into practice at first, when I first started training, and I find out like all this stuff that you never knew like has these side effects that you can leverage to take care of patients. And that's when like an example is Decadron, which is a steroid. It's a very strong steroid. You can give to patients, and it will often help with nausea. Obviously, it's not the first thing that you give them. There's all kinds of very typical nausea medicines that you learn about in medical school, and you trial all that stuff first. But every once in a while, you get a patient where it's like you've done everything, and everything typical, all the standard anti-nausea stuff, and they're still just nauseous. And you're like, well, let's give them a little shot of Decadron, and then they get better. And you're like, oh. It's a reason why these I always felt like those are like the tricks you learn with experience. You just sort of, it's like the ace up the sleeve when you're stuck in the hospital by yourself, middle of the night. It's not a life or death situation. So you're not gonna call someone and wake them up in the middle of the night and be like, sir, my patient is nauseous. I mean, maybe some people would do that, and those people are generally not well liked, but it's like a problem. Like, what are you going to tell the patient in that situation, right? Hey, sorry, I'm the only one on duty tonight, and I don't know what else to do for your nausea, so you're just going to have to suck it up and be nauseous until the morning, and then I'll ask a doctor with more experience than myself then, right? Like that's not really an option. You gotta learn these little tricks of the trade and you remember them from your experience, and you know, it's at least I felt like once I sort of hit a point in my early like like towards the end of my first year, my intern year, where like multiple of those little tricks you remember and like you feel confident enough to just, you know, whip them out and use them, and you don't need to like get someone's approval. You're like, oh, okay, maybe I can actually do this doctoring thing. I can actually, you know, manage to be a little independent in taking care of patients. So I mean, that was always a fun experience when you kind of have a little nugget of independence like that early on.
Sure. Yeah, and
So
it's that apprenticeship model that, you know, medicine is comprised of, even though people might not traditionally think of that. You learn pearls and tricks as you go through.
yeah,
But anyway,
there's a lot of like tips and tricks that are not like empirical medicine. Like it's not data driven medicine, but everyone knows it kind of works. But on the other hand, it's like, what are you going to do? You know, do a clinical trial just to collect medicine or collect data on something that you know works.
Yep.
You don't know why it works. It's, you know, it's hard to collect data to support like everything you do in medicine. But then on the other hand, as soon as you do something that doesn't have data and it goes sideways and, you know, patient gets hurt from it, or, you know, you really start asking yourself, like, how much leeway do we really have to be tinkering with things that we don't really have like good data to support? I don't know.
Sure. Yeah, it's definitely a balance, and you know, we talk a lot about equipoise in that way, right? And achieving, you know, a okay risk benefit ratio, and we could have conversations for hours about that and evidence-based medicine in general, but can probably rein it more into.
We were talking about something similar, right? When I think on Tuesday, maybe with the other Mike. I guess all my guests are named Mike. we gotta find some Carlos. We gotta find some guests out there with a name other than Mike. But you know, he was basically asking me like, "Oh, what are your thoughts on, you know, X, Y, and Z treatment?" And, you know, obviously there's no data for it, or if there is, it's very limited. I don't even remember the question off the top of my head. And so I was like, honestly, you just got to put everything. I think like well-grounded physicians that are committed to like giving good advice, even if they don't know the answer, is like you said, everything's like risk versus reward, right? If the reward is unfounded, there's no data to support that it definitely works or doesn't work, but the risk in trying it is low, like why not encourage a patient to try it if they want to? I mean, I think there's other things to consider rather than just the biological profile, right? There's the financial profile. If a patient comes to me and they're like, I'm trying this supplement and I had to take out a second mortgage on my house to pay for it and I feel amazing. And they're like, what do you think, doc? And I'm like, there's no data to support it. And I was like, if you feel amazing, I guess I'm, you know, who am I to tell you to stop trying it if I don't have like a, you know, a reason to believe it's not safe for you? But on the other hand, it's like, is it the wisest thing for you to be taking out a second mortgage on your house for? I mean, I don't know. Like, I don't know. Like, these are the types of, like, you have to have real conversations with patients about this kind of thing. You know, when you're talking about trialing new things, I mean, I don't think you want to put patients in a box, but you have to have, you know, you have to think about it from a whole perspective and how you counsel them, but ultimately let them make a decision about their own lives.
Yeah, it's this, you know, model of we have to put the patient at the center of the medical team. And I think as, you know, physicians or aspiring physicians, that's a hard thing to do, right? We're used to the ones having the answers, you know, being at the top of the game. Yeah. But at the end of the day, it's a patient's decision to make.
Exactly. And I think especially when you're talking about research, right? I mean, there's a lot of pressure I think especially on academic physicians and
Sure.
researchers to find the next big thing. And you need patients to partner with you as an academic to be willing to accept a calculated risk or a
Mm.
calculated level of unknown to make new discoveries.
Yep.
And I think that can get, as a physician, you have to constantly be reflective on, or a researcher, reflect, or a clinical, a researcher or a physician, or both in your case, who really interfaces with patients is, am I letting my own desires impact how I'm counseling this person in front of me, even if it's just getting their
Yeah.
consent to participate in a trial?
Sure. Sure. Absolutely. And I think that takes us back to this paper. You look at, these patients were undergoing surgery, right, to have the stimulators put in. That doesn't come without, risk.
Oh,
So they're
that's
taking,
actually true. I have to tell you
right.
about a patient that we
Yeah. Yeah.
did epidural spinal cord. Go ahead, finish your thought though. I don't need to interrupt you.
Oh no, yeah. So I mean, you're talking about that risk, and then I think something that a lot of people might skim over in this paper is that it wasn't just that they were being stimulated, but they were working hard while being stimulated. Right? This was physical rehabilitation.
Yeah.
This wasn't a quick surgical or drug-based fix. This was something that required the patient to put in a huge amount of effort
That's
at
actually
the
very true. Yeah. I mean, but I didn't actually, personally, I didn't read it, but they do, they had a whole protocol, a rehab protocol
Yeah, it was something
for,
like 4 to 5 days a week, I believe,
yeah, for like a
of
couple
rehab.
hours at a time. I mean,
Yeah,
it's not a quick surgical fix. Hey, let's stick
right,
a epidural stimulator, spinal cord stimulator in, and turn it on, and bada bing, bada boom, you're walking again. It's
right,
no, like, here's the equipment. Now you have to go through this rigorous rehab process where you really have to work hard, and that's when they started to see the clinical results in the patients. So, and
right.
I think you're completely right. It's very easy to gloss over that fact when reading this paper, because they just sort of offer it as in the supplemental material, like, oh, hey, we have this like protocol that we put all the
Yep.
patients through, which is reasonable, right? You can't include all the information in the article, but yeah, no, you're right. I mean, just enrolling patients in the clinical part of this trial that led to all this like groundbreaking scientific work that we're going to talk about, that's not without risk. We had a patient that we had epidural spinal cord stimulator. I didn't do the surgery. Admittedly, I don't recall all the information about why she needed an epidural spinal cord stimulator. My suspicion would be pain, but I don't remember. Bottom line is, it was supposed to be like a come into the hospital, leave the same day type of procedure. It's not like a fancy surgical procedure where you got to do this big, huge open exposure and so, tough recovery for the patients. I mean, this is a go home the same day type of procedure.
Mhm.
Obviously, once they come out of surgery, we want to keep them for a couple hours and make sure you wake up from the anesthesia okay. And, in this lady's case, I get a call because I was the one taking care of the patient post-operatively. So when she came out of surgery, and the nurse calls me, she's like, I need you to come down and evaluate this person. They could be, I don't think it's a big issue. Basically, she's like, I'm not convinced it's real. I'm like, okay, well, I guess I'll be the judge of that. And, we're in an inner city population. There's, whether disclosed or not disclosed, there's not an insignificant amount of drug seeking behavior among our patients. So, admittedly, there's a baseline level of skepticism in many patients that we see in this hospital. And, it's the patient's basically saying, like, I can't move my legs. And like, oh, that's kind of weird. Like, we didn't do surgery in your spinal cord. We did
Right.
surgery around your spinal cord. Like,
Yeah.
it's possible, but it's very improbable that like an actual like issue was we any sort of issue was ran into with the actual spinal cord. And so, obviously the first thing you do if you want to find out if someone's, genuine or not in their complaint is you start pinching them, right? You distract them like, hey, look over here, slap them in the face. No, not really. But, and she, no response whatsoever. And it was like, all of a sudden, like any concern I had that this may not be genuine just like washes away. And I'm like, something's wrong with this lady. I just start taking her straight down to the CAT scanner. I'm like, I cannot wait. I call, all the people that need to know. And, even they're like, come on, like this doesn't make sense. And, they come down and evaluate her and they're like, no, I think this is real. The problem is that the CAT scan didn't show us anything. But what are you going to do with a patient with a negative CAT scan? No finding on the CAT scan, but as far as anybody can tell, a genuine clinical complaint. Well, she went straight back to the operating room, and sure enough, they found an epidural hematoma compressing her spinal cord, and it was a pretty easy fix at that point. But and these things happen. I don't think it was anybody's fault. I'm certainly wouldn't go so far as to say that. It just happens, unfortunately. There's no such thing as surgery or medicine that's 100% perfect. But, the nice part is the story has a happy ending. She recovered. It was a process, right? Her spinal cord took a little shot, but, with time, everything recovered, full function, no deficits, like a very good outcome for a very unfortunate situation. She was scared. I remember being like really scared, like in tears, like I can't never walk again. Like I love to dance. Like I need to be out in the world dancing. And she was sad. I felt bad. But then it was always like every morning we go see her. Hey, how you doing? She's like, good. I can't wait to dance again. I'm getting stronger. She'd be like, you've been walking out. You could hear her yelling down the hallway. I'm gonna dance. Okay. Well, we're glad you're doing much better. And so as far as I know, she left and everything went well. So, but yeah, I mean, this is a minor surgery, but even minor surgery can go wrong. So, obviously thinking about patient-centered care, even when we're talking about research, So,
absolutely.
All right, let's see. Where do we leave off in this paper? So the first part of this paper, they basically present the clinical situation where they've done this trial of epidural spinal cord stimulation. It's led to clinical improvement in patients' ability to walk. And now they're asking why, how, what's going on. So they decided that the next step was to look at a preclinical model, or in this case, an animal model, a mouse model. They wanted to replicate the disease and the recovery, the rehab recovery in a mouse model, an animal model, so that way it could be studied scientifically and you could start to get to the bottom of kind of what's happening. And so you want to talk about kind of some of the ways that they were able to take this clinical presentation from a human, a person, and kind of copy it into a scientific organism that can be studied, right? Because we can't do scientific studies on humans, right? That would be unethical, right? We'd be in like, early Nazi Germany if we were doing stuff like that, right?
Right.
So how did they take this animal, or how do they take this clinical presentation in humans and copy it into animals so that we can study it? So I'll give you a second to gather your thoughts while I just pause and welcome everybody that's come into the show. If you missed the beginning, I'll just give you a brief update. We're talking about a big scientific research paper that was published in Nature journal last month. Nature, if you don't know, if you're not a scientist or a clinician, Nature is one of the biggest academic publishers, right? They get so many submissions that they get to be super selective in the papers that they publish. So typically they only take the best of the best, the creme de la creme. They put it through a rigorous review process. So in general, while mistakes do happen, it's generally reliable when they publish a really big finding. And Nature basically published this paper that said that they've found neurons in the spinal cord that help in the recovery of paralysis. And so I'm joined by my friend Mike, who is an MD PhD student. So he's both an aspiring physician and a nearly completed training scientist. He's both, as we're sort of talking about this big paper that was published just 3-4 weeks ago. And so we've kind of introduced the first part of the paper, and we're going to get into the next part of the paper. But before I do that, I just want to remind you, head on over to our YouTube channel, our handles down below. We are getting close to 10,000 subscribers. So if you can hit that subscribe button for us, we would really appreciate it. You'll also get notifications every time we go live, which is starting next week, moving to 7 p.m. Tuesday, Thursday, we'll be live next week starting at 7 p.m. So if you want to get the notification when we're live next, go ahead and subscribe to our channel. If you really like our content and you want to support our nonprofit organization, Brain and Spine, well, I guess over here, well, this way, Brain and Spine Group, if you want to support us, you can join our YouTube community for $4.99 a month. It's basically a super subscription. It supports the nonprofit organization. We do not paywall any of our content, any of our videos. It's free. It's open access. That's part of our mission as a nonprofit organization, but we require the support of our community in order to keep doing that. So if you want to be part of that community because you like our content so much that you want to help us on that mission, feel free to join our community. Either way, your subscription means a lot to us. We really are glad that we have you all with us today watching the show. So let's get right back into the next part. We're going to go bring Mike back in. So how do you take the clinical issue and study it in animals? Walk us through what the thought process, at least that you can interpret. Walk us through the thought process that the authors present in their paper.
Yeah, for sure. This is a challenge in studying clinical diseases or injuries in the setting of a preclinical model. So in this case, they were using mice to study this. And the challenges with injury is that in humans, no injury is the same, right? Everybody has, to some degree, a different mechanism of injury or different level of injury and type of pathologic processes, or the bad things that are happening after injury. So with that, they used a model that replicated the most common form of spinal cord injury, and that's going to be one that is brought on by a contusion. So essentially, it's a bruising of the spinal cord. Typically what happens, this might be some sort of a blunt trauma as opposed to a penetrating gunshot wound or stab injury that severs the spinal cord. This is where the bone or other material are pressing up and compressing the spinal cord. So that was the model that they employed here, and they do it in a uniform way because with these preclinical models, we like to have uniformity in order to interpret the results in a similar way at the end. So they use a
Let me clarify one little piece, actually, because
yeah,
I think
sure.
this is an important piece that didn't even occur to me until you were just describing that. What they do is they introduce this contusion, this blunt force trauma that mimics like a typical traumatic spinal cord injury, above the level of the lower part. So basically, they're keeping the lower part of the spine intact. That's the simplest way to describe it. Because clinically, patients, they'll fall off a bike, they'll get into a car accident, they'll break a part of their spine, maybe up in their neck or their mid back, and those bone fragments damage the spinal cord up high, right? And so you lose the ability of the neurons that control walking down in the lower part of the spinal cord, even though the injury is up higher. So the injury is basically creating a cutoff in the spinal cord where things below the level of injury are struggling to function properly. So the injury is not directly to the lower part of the body. And so what they're replicating in this model is they're creating an injury mechanism that is very similar to how humans experience spinal cord injury. So go on.
Yeah, exactly. That's well put. So they do this, and they induce the injury, but then they also needed to replicate both the stimulation model. So they needed to basically develop some modified paddles or electrodes that could be placed above the spinal cord in that epidural space of the mouse. And now you've got to imagine the, just the technical precision that's required to do this, right? Neurosurgery in humans is a very technically precise field. Now you're talking about, reducing the magnification of that to the size of a mouse. That's just.
Do you do animal surgeries in your PhD work?
We do, yeah. So we induce.
Do you personally do them?
Yes, yeah. So
okay.
I induce both brain and spinal cord injury.
Okay, so this is stuff that you personally have worked on.
Yes,
like you've done the animal surgeries.
Yeah, I've done, so the brain injury, what we do is, we basically just cut the cortex. So we take a scalpel and induce a penetrating injury there. And then we do something similar in the spinal cord. So we're not exactly
doing like little burr holes and cranies and lammies in a mouse.
Right.
Yeah, exactly. Yeah. I mean, I did a little bit of that in med school, and honestly, it was like your first experience, like really learning surgery. It's a very I don't know what the word is, inspiring part of being involved in research early on as a student.
Yeah, I completely agree. I think for me too, it was one of the things that, coming into medical school, I knew I had an interest in neurosurgery because I had done some of this work as an undergraduate. So I could at least see that to some degree I had the dexterity, and I enjoyed working with my hands to the point that I could see wanting to make a career out of that. So yeah, definitely a plug for, any folks out there that are aspiring, brain or spine surgeons. When you get the chance to get involved in some research, it's a great way to test some of the physical capabilities of it, or not even test, but just to, make sure that you enjoy working with your hands, because that's kind of the two elements of medicine, right? You have the medical doctors and the surgical doctors, and the surgical doctors have to have a certain level of comfort with, being hands-on in that way.
It is, and comfort is something that can be developed. I think obviously people ask this, and obviously we're getting a little off track from the paper here, but people ask this, I get this question all the time, like, is there other people who are, naturally gifted surgeons? And it's like, the answer, like, yes and no. I mean, there are people who I think learn fine motor and mechanical skills like very quickly, and over the course of a career, they will advance further than other people. But there's no such thing as like a surgical prodigy who just is born knowing how to do surgery. Like, no matter how good you are, you're going to mess it up the first time you do it. Right. I don't think there's, I mean, maybe I'm wrong, but I don't think there's anyone out there who just like picks up surgical instruments and is just all of a sudden some sort of savant. That doesn't exist. But there are people, who learn fine motor skills faster. I think it's the learning process. Right? Everyone sucks the first time they do it. The question is, how much progress do you make the second time you do it versus the third time versus the fourth time? There's people that are going to spend their entire career, they're going to gain a baseline level of skill, and that will limit their ability to go above and beyond. But there are people who learn very quickly and pick up the basics very quickly, and they will far exceed the baseline level of competence.
Sure.
So anyway, go on. We were talking about animal models and that experience and how that translates into this paper.
Yeah. So really key things here, they used or modified an injury model that closely replicated what they were seeing in humans. Again, focusing more on a compression type injury, and then they modified the EES protocol, or the electrical stimulation that was being inserted above the spinal cord, so that they could have a device that mimicked what was happening in the humans, but now at the level of the mice. Some other important things. So part of the rehab that they were doing in humans was having a model of kind of weight support, and that's required for the rehabilitation process to occur. Right. Once you start the epidural stimulation, that patient's not going to be able to be weight bearing on their own. So they have to have this weight support, essentially a harness that straps them up to the ceiling. That way they can use the muscles that are being stimulated ultimately, even though they don't have the strength yet in those muscles to be weight bearing. So they essentially created, mini harnesses for the mice to be able to accomplish that. Another interesting thing here is that they tested, with motor cortex stimulation in order to mimic the voluntary nature of human rehab. So it's pretty cool using some optogenetics approaches to actually be able to turn on signaling from the brain down to the spinal cord. That way they could mimic what a human would be able to respond to kind of on command from their therapist. So that was, some of the core elements that went into creating this model and employing it in the rest of the project.
Yeah, so for anyone that's joining that didn't see the beginning, I want to just make sure you're able to stay up to date with kind of what we're talking about. So I just went ahead and put the journal and the name of the article that we're talking about on the lower part of the screen for you if you want to check it out and follow along. This is what we're discussing today. Kyle, welcome to the chat. Thanks for joining. We appreciate you saying hi. Anyone else out there, comments, questions for me, for Mike, leave them in the chat. We're happy to answer them. But my comment on what you were just saying is, the the challenge of looking at voluntary motor control, meaning like me as a human, I want to do something, right? I decide, put my hand up, and I put my hand up. Now, obviously, if you really get into like really deep behavioral neuroscience, there's people who would argue that that's not even a voluntary action, but that's not what we're talking about here.
Mm-hmm.
I think, was it some studies or something that show like the brain decides it wants to put its hand up before I even can understand that I want to put my hand up or something. I think those I forget how old these studies were, but there's anyway, that's what I'm referencing. There are some behavioral neuroscience studies that suggest that we don't even have voluntary control and that the brain is actually truly in control. And that our cognition is just like an afterthought of the brain's premeditated action. I think it's something like that. It's kind of freaky stuff. I remember learning.
That's giving me some Inception vibes there.
I mean, that's kind of what these studies are about. I don't remember all the details. I had this like sudden flashback to like when I was a undergrad student and taking this behavioral neuroscience class, and somebody is walking us through these studies, and I was just like, whoa. Anyway, so an important part is being able to recreate the phenomenon of voluntary motor control in an animal model, which clearly we cannot communicate with, right? We cannot ask the mouse, please lift your leg. Whereas a human patient in rehab, we can ask them, please lift your leg. And they can try to lift their leg up, and their ability to control that action gives us feedback as an evaluator how effective the therapy is. Now, a mouse or an animal model, we don't have the ability to do that. So basically, what the authors did to circumvent that is they created these genetically modified mice, which is far more common than you would probably realize if you're not a scientist. That did you explain? While I was putting up the title of the paper, if you explain it, did you kind of explain how the authors accomplished that?
Yeah, so I can actually share over if you want to an image.
Yeah, go ahead, share
to show the optogenetics
to me,
stuff.
this is like a very cool concept, even though it's very common to like scientists. I think for people who are not scientists to kind of realize like the capabilities that we have in the lab, this was kind of mind blowing. I remember learning about like this technology, optogenetics. Is that what you're getting ready to explain?
Yeah, exactly.
Yeah. I remember learning about optogenetics in undergrad when it was still fairly new. Like not many people did it, and like Cornell like just got their first like neuroscience faculty hire who was like trained in optogenetics from their postdoc, and he was the only one doing it, and it was like everyone's like, oh my gosh. Anyway, let's besides that, go ahead, let me turn your screen on. Let me turn this off so that way it's a little cleaner. We'll turn it back on in a little bit. Go ahead.
All right, are you guys able to see my cursor here?
Yeah, all looks
Okay.
good on my end.
Beautiful, beautiful. Yeah, so optogenetics is something that, as a neuroscience student in the last decade, I mean, you really had the chance to see a technology as it was, burgeoning and becoming more common, which is super cool. And that's one of the great things about science is that, what you learn during your undergrad or your medical or graduate school is not necessarily what you're going to see when you're out in practice. There's going to be that plus more. And this is just a great example of that kind of technology. So essentially what's happening here is we can put the gene, coding for channel rhodopsin, or a receptor that's responsive to certain light stimulation. We can put that into the genome so that it's expressed within specific cell types in the mouse.
Let me
And
translate that for everyone.
Yeah.
Right? There's a lot. So Mike just dropped a lot of like science technology. Let me break this down, as we say in the Marine Corps, Barney style. So basically, what you're doing is you're telling an animal's genetic material to create and embed a light switch into specific cells, right? So you're basically able to genetically modify the animal so that the animal's own body manufactures and displays a light switch in very specific locations. And then once the light switch exists, then the scientist has the ability to just flip it on and off. And so you can literally manipulate cells within the animal that you cannot normally do. Does that kind of cover it, at least from your perspective, Mike?
Yeah, that's perfectly put. So, with that, now we have the ability to turn on a neuron or turn off a neuron, which would be the opposite case shown here on the right, under specific circumstances. So what they were able to do here is, while the mouse was receiving that epidural electrical stimulation, or that stimulation above the spinal cord, they were also able to stimulate and mimic the voluntary motor control that would be coming from the part of the brain that generates voluntary movement. And they were able to mimic that and have this neuron turned on, so that we were getting both the input from the stimulator as well as a mimic of the input from the brain itself.
So basically, by flipping the switch with light, the scientist is able to manipulate the mouse's brain into saying, I want to lift my leg up, just like
Exactly.
a patient would do if a patient wanted to voluntarily say, I want to lift my leg up. When I read this, actually, let me pull up my screen real quick.
Yeah, sure.
It reminded me of this, one of my favorite video clips from Scrubs. Are you a Scrubs fan, Mike? Or is that
yes,
beyond your generation?
I love Scrubs, except for the last season. It was a little.
It was its own show. I'm a huge Scrubs fanatic. I mean, literally, I've watched it was like a ritual. I would watch every season of Scrubs every summer, pretty much every year, from high school on until basically third, fourth year of med school. I started running out of time to do it, but it was like a summer tradition. School would let out for the summer, and I'd watch every season of Scrubs throughout the whole summer. So I've probably seen the whole series 8 or 9 times.
Awesome.
Anyway, so when I read about their ability to literally just manufacture voluntary motor control with optogenetics, I was like, this is literally like Michael J. Fox on Scrubs. Let's pull it up. Carlos, we might have to mute this because of copyright, but we'll play it on the show. Oh, hold on. Let me we have to probably there we go. Audio should be on now. All right, let's hit it.
And the surgeon in me is antsy.
Oh,
to cut somebody up.
Let's back it up. My screen's going all haywire. Turn the volume up a little bit.
I need to cut somebody up. Thanks for volunteering. I'm not really that strong on the brain. I think this is the language center.
Really? Because I don't feel a... How cool is that?
And this is the foreign language center.
Impossible, je n'ai pas arrosé.
The cow says. The sheep says.
Bah!
Ladies and gentlemen, Macaulay Culkin.
A French would help.
So, I mean, in essence, that's basic. I mean, the last scene, where he goes, ladies and gentlemen, Macaulay Culkin. I mean, that's basically what the scientists are doing in mice, right? Except instead of surgically being in their brain manipulating things, which, for the record, we do not do as clinicians. This is this is 100% parody, albeit hilarious. But that concept of like this scientist controlling the motor behavior of the mouse and making them go like this, even though you could make the argument it's involuntary, right? But you're basically making the brain tell the body to do a voluntary motor action, right? That's the gist of what's going on here.
Exactly. I do want to hit, so Kyle has a question in the chat here.
Oh, yeah, here we go. I pulled it up for you. Go ahead, answer his question.
Perfect. Yeah, so this is a great question, and it actually ties directly to the paper. So the intensity of the light or the laser, being used in this case, does indeed modulate the signal. And actually, what they showed here is that depending on the laser intensity that was used in the motor cortex or in the part of the brain that generates movement, that produced different step heights for the mice. So essentially, they would take larger steps with higher intensities of the laser.
And that ability to increase how much of a step the mouse or the patient is taking is a marker of voluntary control. Because if there's no voluntary control, then what that means is that it's becomes more of like a motor pattern. Like imagine a little wind-up toy. You just kind of wind it up and, the little mechanics make it just go, and it takes the exact same steps because it's just a mechanical stepping pattern. I mean, that's a very simplistic explanation, but that's basically, that is a possibility, right? And that would indicate that the walking function is more reflex mediated as opposed to voluntarily mediated, which is kind of a complex concept if you're not. I think that's put in a relatively simple way for someone who's has a physician's training, but if you're not a scientist or a physician, that might seem a little complex, but I don't think we need to get too wrapped around like further details about that. But there is a difference. There's a difference between like reflexive motor patterns and that sort of like wind-up toy that just goes versus that like cognitively controlled, voluntary, like I want to move my legs, so I'm going to walk. And the way that they're sort of differentiating that is like if the patient says like I want to lift my leg higher, they can just lift their leg higher, right? Whereas like if it's a reflex, it's the leg is just going to lift the same way every time. Basically, it's a pattern. That's at least how I interpret it.
Yeah, for sure. There definitely are more details that we could get into, but I think it's beyond what we need to.
We have a question from Kofi McNair, kind of like a cognitive function. If you're referring to the voluntary control, that's exactly what we're getting at. We're saying like they needed to prove that the motor control is voluntary. It's a cognitive process where the brain says, I want to move, I'm going to move. Whereas the whole point of a reflex is there's no cognitive process involved. And that's because if you look at known reflex arcs, they don't actually go through the brain, right? Like a simple patellar reflex. You go to the doctor, they hang your leg off the side of the exam table and they tap your knee and your leg shoots out. You don't control that. It's a reflex arc that never goes to the brain. It goes solely through the spinal cord and that's it. And so what you want to do is make sure that when you're looking at walking, you're not looking at an advanced reflex circuit where the legs are kind of walking and the brain has no idea what's going on. You want to confirm that the legs are walking and the brain is turning it on.
Right. And even our brains do a little bit of those patterning things. So
Yeah.
the classic example, right, is if you're going upstairs and the stairs are all at the same height, but then that one throws you off because it's a little bit higher, a little bit lower, right? You're not, directly thinking about how high you're lifting your legs to climb those stairs. It becomes a kind of repetitive pattern. So there is a role for some of those patterns, but what they really wanted to test here was that you were essentially able to start linking up some of that brain voluntary control with the spinal cord kind of through the injury.
All right, so we've kind of really beat to a pulp this idea of how they took what they're seeing in patients and replicated it in animals so it could be studied, and then sort of confirmed that their replication in the animals is like true to the form of how it's displayed in humans and isn't like a mimicker. It's like it truly demonstrates the situation in humans. So now all we've done is really set the landscape. We've kind of created an environment in which they can actually do their experiments, because we haven't even really got into their experiments. All we've really done is like explain how they've created an optimal environment to then create a series of tests and things like that to discover things. So let's see, what should we get into next? Possibly this idea of like molecular cartography, I think is so. Basically, now this is what we should talk about next. We've talked about how they've created what I consider like a blank treasure map. It's like, imagine they've rolled out the piece of paper, they've smoothed it out, they've got a nice environment, but there's nothing there. It's just a blank treasure map where they need to now kind of start mapping things out and actually figure out where things are. So before we get into that, I'm just going to go ahead and pause for a second. If you are just coming in, welcome. We're glad you're with us. Let me just give you a quick reminder. This is what we're talking about, a paper in Nature titled "The Neurons That Restore Walking After Paralysis." Flashy title. The question is it legit? And that's what we're diving into. We're breaking down sort of this step-by-step, the process of this paper to figure out if it really is exciting, nature-worthy stuff, or really more of a headline that doesn't tell us too much. So far, it's seeming pretty good. I'm pretty amped about what we've been getting into. Before we move on, though, we would really appreciate it if you take a minute, go over to our YouTube channel, subscribe, because we're getting close to 10,000 subscribers. So if you like the content we're doing, subscribe so you get a notification every time a new video comes out. We go live every Tuesday and Thursday. Next week is going to be at 7 p.m. We're going to see how the 7 p.m. time slot works out for everyone. So you'll get a notification next week when we go live. We also upload videos regularly. We have a fantastic YouTube producer who helps create educational videos from our seminars, clips from our live streams. There's tons of stuff over there on the YouTube channel. So if you could subscribe, help us get to those 10,000 subscribers. That would mean a lot to us. If you really want to support the production of our content, we are a nonprofit organization. The way you can do that is through joining our YouTube community for $4.99 a month. It doesn't give you access to any new content because as a nonprofit organization, we are committed to keeping our content free and accessible to everyone. We do not want to charge or create barriers to accessing our content, but we do rely on the support of our community in order to keep doing what we're doing. We've got a lot of great things coming in 2023 that I think it will be very exciting for our supporters to get behind. We're making a big effort to not just create educational content, but to empower research teams to actually move some of these ideas and research projects forward. We're getting out into the community, trying to help veterans with brain injury, patients with brain and spine illness and disease. We are getting involved in our community with one goal in mind, and that's to improve brain and spine health. So if you want to get behind that mission, join our YouTube community, subscribe to our channel. And if you really want to make a huge impact, you can go to our website, www.neurosurgerytraining.org/donate, and you can make a financial contribution. We would greatly appreciate it. So with all that information out of the way, let's get right back into the show. So now we're talking about how do we actually create a path? Because I read this next couple sections of the paper, and my thought was actually the way I sort of envisioned it. Have you ever seen the movie, the first one, National Treasure, Nicolas Cage?
Oh, of course, great movie.
Right. I mean, it's a great movie. I remember the scene where like they just stole the Declaration of Independence, and Nicolas Cage is like, "There must be a map," and it's like all the clues tell him like, you know, he can't see it, but like I know it's there. And then all of a sudden they like whatever start like rubbing lemon juice all over the back of the Declaration of Independence, and sure enough, like these clues start coming up. That's kind of how I envision these next couple sections of the paper. It's like they've kind of said, based on the clinical data, based on what we're seeing in the animals, there must be some like X marks the spot location in the spinal cord, but we have no idea what it is. So then they go through this series of experiments to basically help identify like where is this hidden X that marks this treasure chest of, you know, this like population of neurons contributing to unlocking the explanation for this clinical phenomenon. At least that's how I kind of played it all up in my mind as this big dramatic story, because, you know, it's a nature paper. If they're not telling a story, what are you doing?
Exactly. Yeah, and it, you know, exactly what they're doing here is they're putting the lemon juice and the heat right on the back of the Declaration through a couple of different techniques so they can expose that. So, you know, one of the first ways they went about it was to try to look at how the expression of you know, certain genes, or essentially the conversion of genes into proteins, changes after this rehab model. They used a technique called single nucleus RNA sequencing. So, you know, kind of a big term just to say that they took individual cells and then they took the nuclei, right, or the central portions of those cells that sort of act as the brains of the individual cells and contain the genetic material. They took those nuclei and they separated them out in order to do sequencing. So they wanted to determine not the sequence of the genome or the code that you know, produces RNA, but they wanted to measure the RNA itself. They wanted to measure this product from the genome or from that genetic material to see how its production was changing after the injury in the rehab model. Single nucleus RNA sequencing is a pretty, you know, new technique. It's, you know, been becoming more common in the past couple of years. It has a lot of benefits compared to things like bulk RNA sequencing, where you just take a mass of tissue and you break it down, you break all the RNA from it, and you look at how the overall tissue is changing in gene expression. Here, you're able to look at a single cell level and say, how is neuron A changing compared to neuron B? And that was the key to being able to carry out.
It's like high def TV versus like you know, some old tube based system from like the 80s.
Exactly. So they do this RNA sequencing, and what they end up seeing is that there's different clusters of neurons that are responding differently to the rehab model. And they specifically identify through a combination of this RNA sequencing and then some spatial transcriptomics, which is just a fancy way of saying now they're taking the entire tissue and they're measuring the production of RNA, looking at a slice of tissue in the spinal cord. So they can start visualizing where exactly in the spinal cord the expression of that RNA is. So
this is the spatial transcriptomics that they discussed, or they describe. Yeah,
exactly. So they do that, and they end up identifying this. I think it was a group of HOXA10 neurons that appear to be the primary responders to the rehab model. So they have, you know, the largest degree of change after the epidural stimulation combined with rehabilitation.
So they basically find, like, I'm trying to think of like the most succinct way to describe this. They basically find a subpopulation of neurons. Like if you think about it, like imagine there's like 10 identical twins and you just sort of like release them out into like a busy street in Manhattan, right? They all kind of like look the same, but you can't actually see that they're all twins unless like you get them all to like hold their hand up in the middle of a busy street, and then you kind of like look around and you're like, oh yeah, they're all the same.
Right.
That's kind of the gist of what they're doing.
Yeah. On the surface, all these neurons are going to look relatively similar. So now we need to identify, what makes them in the way, and that's through the changes in the gene expression that are happening.
It's like a giant Where's Waldo? Except you got like 100,000 Waldos buried in the spinal cord.
Yep, exactly.
So that's what this is based on. This is basically trying to figure out, what is who's the Waldo among millions of neurons. Now they've figured that out, and as you said, they have to figure out like, okay, what's special about Waldo?
Yep.
And obviously, where's Waldo? He's got a red hat with stripes and glasses and blue pants or whatever. You can describe him, and then every time you see him somewhere, it's very characteristic. So now we basically have this like neuron with no description, right? We just know that it has has a population with consistent characteristics, but we don't know what those characteristics are. And so there's two technologies that I sort of vaguely understood. And now we're really getting into like the weeds of like scientific technologies that even myself as a physician, like I can read the paper and I kind of get the gist of it, but I have not been in the lab. I haven't used these technologies or used similar technologies. So if you ask me like, what does it look like? I mean, the extent of like my lab experience was basically like immunohistochemistry, which obviously is not what we're talking about here, but is pretty a pretty primitive like lab technology experience kind of guy. So they use this thing they call auger, AUGER, that they describe as a compass for transcriptionally perturbed neurons. So my understanding, and correct me if I'm wrong, this technology is basically like they know there's this population of neurons out there that respond to this therapy. They sort of know that it responds in a transcriptionally protein producing modified way, right? So when you do this therapy, it changes the way that this subpopulation of cells behaves. And this is basically like this technology is like a compass that literally just sort of like points you at the population that's disturbed. Is that kind of what's going on here? That was my interpretation of it.
Yeah. So, you generate this data in terms of, essentially being able to look at all the RNA or all of the gene product, right? How the gene expression is changing. And you can see which population has changed the most. And that's what they use this essentially a computer algorithm for. So it's a form of machine learning, which is obviously a really hot topic right now, not only in research, but in other industries beyond that. So they write this code or this program that allows them to identify the most perturbed or the most distinguished population from there.
Okay. And then after they are able to basically be pointed in the right direction of these changing neurons, that's when so basically what they do is they're using I'm just referencing my notes here on the side because now we're starting to get into the weeds. So they use the epidural spinal cord stimulator to induce change, to perturb the neurons of interest. Then they use this technology that basically points them towards the perturbed neurons. Then they talk about this thing that they developed called the Magellan, which then basically, my understanding was kind of confirms the location of where the compass is kind of heading, telling them to go. Like the compass kind of tells them what direction to go in, but then they need to know, like, do I walk 300 steps west to east, or do I go 5 miles? This sort of tells them, like, this is where you need to, like, you need to go in this direction, and you need to kind of go this far to actually find X marking the spot on this treasure map. Is my interpretation of that, like, accurate?
Yeah, so you can think of, I think the auger as being this mechanism that points you to this is the population, and Magellan now it says this is where the population is in the context of the rest of the spinal cord. So it gives you that spatial information that allows you to say, X marks the spot. Not only is it this population, right? We know we've identified the treasure, but it tells us where in the map the treasure is.
I see. So it's almost like Auger tells you the characteristics of Waldo, right? He's got red hair, he's got white stripes, blue pants, glasses. Magellan tells you this is where Waldo is living.
Right.
And there may be other things living in that location, right? So you get there and you're looking around and you're like, okay, there's 100 people around, right? You can't just go, which one to use Waldo, right? You got to look for the one that you got to go to the location, and then you got to find the one with the characteristics of Waldo.
Yep, exactly.
And so, I mean, this is got to be years of not just doing scientific experiments, developing technology that didn't previously exist to then actually conduct the experiment.
Right.
I mean, it's impressive stuff, at least from my perspective. Are you impressed by it?
Yeah,
Okay,
I'm always impressed
I'm
always impressed to read some of these nature papers, just when you look at the number of, figures that they have, right? And, kind of for the lay audience, the figure represents sort of each experiment in some ways. It tells you this is what we did and this is what the result was.
Pull up some figures while you go ahead. Yeah. Keep going. I'll pull up some figures so they can see the complexity of these figures.
These figures are super complex. They're multi-paneled. They represent, probably hundreds of individual experiments.
I mean, this is just figure one, right? So it's multiple panels, panel A, panel E. This is just describing the epidural spinal cord stimulating process, the process of rehab, process of translating this into an animal model, this sort of replicating the effects of epidural spinal cord stimulation. Because we didn't really talk about it much, but they basically showed that the spinal cord stimulator actually decreases neuron activity, and through decreasing neuron activity, increases motor activity.
Right.
I mean, and this is literally just the first figure.
Yeah, huge amount of data that's being presented here.
This is the cartography we were discussing, where they sort of take this cross section of a spinal cord, and now they're starting to locate, to identify the characteristics of the neurons, and then start finding the locations of these neurons. I mean, this is impressive stuff. Was there a specific figure you wanted to look at? I know I just started randomly pulling up figures.
No. I think looking at the sheer mass of figures that they have and the data that comprise these through them.
I mean, these are extended data too. So like these figures here, they're like, they didn't even include in the actual, hold on a second. I muted Ryan's screen. Carlos, what's going on? Oh, there was a double audio. Hold on. We can fix that. Sorry about that. Okay. I think we're fixed now. But extended data, I mean, these are figures that weren't even in the actual main paper. They had to basically say, like, we can't even fit all this information in the main paper. But I assume, honestly, I assume the main purpose of like extended data and all that kind of stuff is because the reviewers really need that information to clarify and substantiate the legitimacy of the work, but it's not as important for communicating the outcome of the report. Is that kind of what, like, the purpose of extended data here?
Yeah, exactly. So it doesn't tell the story itself, but it makes you more confident in the story being true in a way. So a lot of times the extended figure will include, or the extended figure will include kind of the validation that was required to prove that each experiment was actually testing for what we claim it to be testing for.
Extended figure 14, 15.
Yeah, it went up to 15 extended figures.
There's like 15 figures in every single figure. I mean, just look at the raw amount of data in these figures. I mean, it's impressive. This is a lifetime of scientific work.
Yeah, we always laugh in graduate school as we're going through, what we consider some of the classic papers in whatever field it is. For me in neuroscience, because you look at some of the papers from the 80s and 90s, things that are characterizing phenomena that we now recognize to be true, and the phenomena that are responsible for core biologic processes. So I think I took a class in molecular neurotransmission where we were essentially studying how neurons communicate to one another, and we read through some of the papers that describe the machinery responsible for that process, and 4 or 5 figures max. But they were publishing in Nature or in Cell or some of these top tier journals. So you see how rapidly science is evolving, and it's getting to the point that to keep up, you need to be able to put in 15 supplemental figures on top of the core figures. So it's just science. I don't want to say it's getting harder, because I think we have more knowledge to build off of. But maybe it's becoming more rigorous. It requires you to really
becoming more granular, for sure.
And more granular,
right?
For sure.
I mean, even just the scope of specialization of a researcher now compared to 30, 40 years ago. I mean, a clinically practicing neurosurgeon did far more research, like true scientific research, 50, 60 years ago than
absolutely
a clinically practicing neurosurgeon now. Now, obviously, there's tons of hospital system, business of medicine, environmental factors that probably play a role in that. Clinically, I suspect the busiest clinical physician, I mean, I could be wrong about this, I'm sort of speculating, but I would postulate that the busiest physicians today are far more busy than the busiest physicians from 100 years ago. I mean, Harvey Cushing was the first neurosurgeon. He was in practice early 30s, I think. So neurosurgery as a specialty is probably just barely less than 100 years old. If I'm I'm sure there's more accurate information out there. I'm just sort of spitballing based off the top of my head. I haven't reviewed any history of neurosurgery papers recently. But I have read Harvey Cushing's biography I forget who the author was. It was very good. I enjoyed it very much. I read it probably close to 10 years ago. But the amount of time, like how busy they were clinically back then, I'm sure drastically different than today. And so obviously their investment in research and science was probably much higher back then than it is today.
And I think back then, just doing the surgery itself was research, right? You were, you had to study your patients so carefully because you might have been doing procedures that no one else ever did. I don't think there was, such thing as a bread and butter neurosurgeon, because brain surgery wasn't bread and butter. Not to say that it is today, but we all know that there are cases that have been
Relatively
well described,
speaking,
and you know how to do them and what the outcomes should be. What's the saying that the only minor surgery is the one that somebody else is doing or having, right? I think every surgeon needs to
the
think
only
what they're
minor
doing is
surgery is the one
major.
you're not involved in.
Exactly. But yeah, everything was major, whether you were doing it or not, in the early days of neurosurgery.
Mm-hmm. Mm-hmm. All right. Well, should we keep moving through this paper? I think there's a couple more things. So basically, if we talk, I think we've moved through about 2/3 of the paper. You know, we've gone just to sort of rehash the signposts of things, right? They started by identifying this clinical phenomenon of epidural spinal cord stimulators improving motor function in spinal cord injury-induced paralysis, right? Obviously, you can have paralysis from a whole host of other reasons, but this is specifically to spinal cord injury-associated paralysis. You know, they saw that epidural spinal cord stimulation aided in the rehabilitation of motor function. That was the clinical phenomenon observed. That's led to the researchers saying, well, let's explain why. They did that by first creating a reliable animal system in which they could study it. Then they took that animal system and they created a map that led them to a very specifically identified cell type and location of that cell type that was found to be the causative or presumed causative agent as to why this therapy was working. Well, we don't have to get into the details of why. They kind of talk about like, oh, they observed all these different things related to, you know, this location and population of neurons that explains why. Now they needed to test, okay, can we create a bunch of different scenarios that support that it's truly this subset of neurons that actually yield the beneficial effect of epidural spinal cord stimulation. And so they did that. Oh, I'm sorry. They did that a couple different ways. I think they first created so I think the first thing they did, right, is they knocked out the function of these neurons in healthy animals, so animals without spinal cord injury.
Yep.
And they showed that this identified population of neurons that they are hypothesizing or speculating is improving a patient's ability to walk. They showed that if you basically remove these neurons from an animal that does not have a spinal cord injury, that it doesn't actually impact their ability to walk.
Yeah,
Right?
and you know that's a fascinating finding because it's essentially saying that you have this group of neurons that, you know, maybe we don't really have their function well characterized in a healthy mouse, but for whatever reason they're playing this important role in the response to and the recovery from spinal cord injury, you know, with this specific treatment modality.
So basically, we don't know what their actual like intended function is. We just know that after an injury, when you give epidural stimulation therapy, this set of cells all of a sudden gets recruited. They get pulled in to help recreate voluntary motor function of the legs.
Right.
So that was the first thing that they showed. When in sort of now, I guess now I would kind of say we're in like the validation of findings phase of the paper, right? We've sort of established the question, the clinical phenomenon in part 1. Part 2 is sort of like, how do we identify the cause of that clinical phenomenon? And now part 3 is, how do we validate that the finding from part 2 is actually true? And so that's now what we're doing is going through like a series of like, how do they validate that these neurons, like this is true? And the first thing they showed is that the intended function of these, you know, cells is not in walking. It's like cells that are involved in some other unknown process get recruited by epidural stimulation to help rebuild the walking function, which is kind of interesting.
Yeah, for sure. The validation, of course, from a scientific perspective is super important. And there are some interesting things they do here. So, for example, they show using, again, that optogenetics or that ability to turn a light switch on or off in these specific neurons. They show that they're able to essentially replicate, or the term they use here is phenocopy. They're able to replicate the impact of the epidural electrical stimulation just by turning on this group of neurons that they identified. And to me, that's the ultimate, kind of confirmatory test, is that even in the absence of the external technology, you're able to replicate the effect in an endogenous or using the body's own cells type mechanism.
Yeah, I thought that was super cool. So they basically use genetic modification to take that light switch that we talked about earlier, implant that light switch in this like newly identified population of neurons, and then they say, to hell with the epidural spinal cord stimulator. We don't need it. Get it out of here.
Right.
And they basically flip the light switch on for these neurons and show that it has the same effect as if they had epidural spinal cord stimulation. So now we've basically shown several layers of validation. One, that, well, actually, I don't know if you would put the whole, showing that these neurons aren't involved in like walking function at baseline really in a validation category, but it helps to better characterize like what are these neurons actually doing.
Yep.
So then after they do that, they also didn't they or actually they use chemogenetic activation, right? So, or maybe we got that wrong. Did they use optogenetic, like
So I think they
method, or did they just use that to turn it off? Or maybe they did both.
So I think it was a combination. I think they did the optogenetics, which provides that more acute stimulus, and then they also did this chemogenetics, which was more of the chronic.
What is chemogenetics? I don't actually even know.
Yeah, so chemogenetics is kind of the same idea as optogenetics. So you're putting a piece of DNA that codes for a certain receptor, but instead of that receptor, or what we had previously called a light switch, instead of that being turned on in response to light, now it can be turned on in response to very specific applications of drugs or small molecules that can be injected into the animal.
I see. So it's basically doing the same thing two different ways to show that, like, hey, we tried it once, we confirmed it, now we're trying it again, we're going to confirm it again.
Right.
And they're like, okay, this worked twice, two different ways. Hold on a second. Why do I what's going on here? Something's going on. Carlos, are you messing with the screen? It keeps changing here. They basically, okay, so maybe our software is just bugging out. I don't know why that screen keeps popping up. Or maybe it's because I need to turn this off. I don't know. We'll see. So basically they said, confirmed it once, got it. Confirmed it again. Okay, now we're very confident. Like this is it, right? Like this is the culprit. And then they tried to circumvent these neurons. I forget how they did it though. What was it was like one of the very last parts of the paper. I just have in my notes here that they tried to circumvent use of this neuronal population. I forget exactly how they did it. Let me see.
So are you thinking of the experiments where they optogenetically or chemogenetically turned them off?
No, it was after that. They said, let me see. Blah, 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 blah. Oh, they did a lateral hemisection. So I think maybe I'm not understanding this 100% correct, but I think they actually maybe even then did a third. Basically, so they turned it off with they turned this population off with a light switch, optogenetics. Then they turned it off with genetic modification, chemogenetics. Then they turned it off, I think, mechanically by mechanically slicing the spinal cord and saying like, okay, fooled me once, you're not going to fool me twice. Definitely got to make sure you're not going to fool me 3 times. And they said after that, I said, okay, we've validated these findings. Like this works. This population of neurons responds to epidural spinal cord stimulation and improves voluntary motor control of the lower extremities in patients with traumatic spinal cord injury. So now what does it do? No, go ahead. Make your comment.
Just to finish up on that point. So the hemisection experiment, so at least in mice, a hemisection should not result in complete paralysis, right? And there should be recovery of walking that does happen. So what they were doing here is, rather than testing to see if the epidural electrical stimulation would result in recovery from that complete injury that we were seeing before, now they're looking to see that even in the absence of that electrical stimulation, if this is the neuronal population that helps to deliver the recovery that we see normally in hemisection. And that was indeed what they saw. So this basically confirmed that this neuronal population is important for the normal, or what I call endogenous, response to traumatic spinal cord injury.
So basically what they're saying is, now we went back to see, in a clinical scenario where we expect recovery, is the recruited population of neurons in epidural spinal cord stimulation the same set of recruited neurons in a more natural recovery process? And they used hemisection to represent the more natural recovery process.
Yep, exactly.
Got it. All right. So then now all right. Now the moment of truth. Quality or hype? What do you say?
Yeah, I would say just in, again, the sheer amount of data that's presented here, is a testament to the quality of it. This by no means, says that a patient can go tomorrow and get this EES put in and can expect to walk again, right? And I think, it's important to recognize that they had, 9 patients total. I think there were a handful of patients who were sensory motor complete, or lost both sensation and movement after injury, whereas there were some that were motor complete only, but still retained some sensory function. So we did, see this heterogeneity in patients being different at the baseline following their injury. That could potentially play a role in differing the outcomes that are expected to be seen. So I wouldn't say it's a hype, but it's not going to be something that patients tomorrow are going to benefit from. What this does do is it drives
that was my
the
next
need for
question.
future
what do you
research.
think this means for patients?
Yeah, I think it's something that could come down the road in the next several years as being effective if the clinical future larger clinical trials show it to be an effective modality. And again, we get back to the point of, this is not going to be the quick fix that folks are looking for in a lot of cases for spinal cord injury. It requires a huge amount of patient and provider effort with the rehab. And I think a lot of people know that there are challenges for patients in receiving the intensive rehab that's necessary, as well as challenges in patients wanting to put themselves through that. They've already been through a traumatic experience of being injured, and now you're asking them to go through a potentially traumatic experience of undergoing rehab. But what this does show is we can potentially use this EES as a measure to augment the effectiveness of that rehab therapy.
Do you think that, well, from like a more of a scientific perspective, right? So this study, going back to one of the original things we discussed, right? This study went from the clinical bedside to the bench to kind of explain what was being observed clinically. Now, how do you take this bench information and ask the next question to work forward towards the next translational possibility for patients, right? Because obviously we're already clinically trialing EES, right? We can work forward clinically based on what's already known about EES.
Right.
Now that we have this kind of scientific explanation for the mechanism of EES, how do you use that to now go back to a translational project? Like, what's the next translational project in hopes that it will lead to something different clinically rather than just helping validate something that already exists clinically? Is it like, my mind just goes like pharmacologic, right? Do you work on a drug that can target neuronal activity of this subpopulation, like a very highly specialized pharmacologic agent? So instead of getting intermittent epidural electrical cord stimulation, you're taking a pharmacologic agent that targets the exact same neurons in the exact same way, and induces the same biomolecular response that stimulating these neuronal populations is doing, except instead of needing a surgery, instead of needing it constantly turned on, you're literally just take a pill. And over time, those neurons help rehabilitate, obviously along with physical rehab, right? But you need to discover that pharmacologic agent. I mean, that's where my mind kind of goes. Like, where does your mind go as a up and coming scientist, right? Because in many ways, this is a lifetime of work, right? The person who created this paper, right, this Nature paper, at some point was a PhD or MD PhD student in your position, reading all the current literature, trying to ask questions about how they are going to basically create their career going forward. So that way, by the time they get 20, 30 years into their scientific career, they've created a body of work like this. So in many ways, I guess what I'm getting at is you're in the perfect position to be asking yourselves these questions of like, how am I going to predict the future as to like what the next big thing could be that I'm going to spend the rest of my scientific career trying to prove and substantiate. So if you took this paper and said, okay, what's that? What am I going to do? How would you, like, what sort of things are going through your head?
Yeah, so I think you can approach it from, a couple of different avenues. So you brought up the good one in being, a potential pharmacologic agent. We know that pharmacologics drugs have side effects that can be a challenge. So is there a way to maybe deliver a targeted drug therapy or a targeted pharmacologic therapy? We can also look at it from kind of the biomedical engineering or biotech perspective of how can we make the device smaller, more convenient, a battery that lasts longer. That way, even if you have to have the device remaining in, how can you limit the need to interact with the healthcare system once you've gone through that intensive rehab, but still have an effective agent or an effective
tool? Because then that's where you can take an existing technology and make it more adaptable to, like, in a global setting, low resource settings where they don't have consistent follow-up and intensive rehab programs. But if you could create the device to function, or you get somebody in, maybe they need a surgery, they need a recovery, and they can go back to working in the sugarcane fields for the next 30 years, or I mean, maybe not, but then at least you're taking an existing technology and you're adapting it to be more applicable in other scenarios. Because we are a little bit privileged here in that in a first world economy to be able to take advantage of these types of things.
Yeah, absolutely. And that, that's a personal interest of mine, is the global health perspective on some of these things. We saw even a little bit of backlash after some of the new released WHO guidance on brain tumors, because so much of the classification became dependent on molecular markers of tumors that just, aren't a reality.
You
And
can't
some
do it
of
in the middle of a desert or something somewhere.
Right, exactly. So I think, as we're making these scientific advancements, we do want to be thinking of how we can disseminate them in an equitable way, but also how we can, to our best ability, maintain and provide improvements in those low and middle income countries where some of this isn't possible. So, it definitely needs to be a dual approach. We can't be saying that we shouldn't make advancement because our effort should be put to creating equity, but we also need to recognize the need there.
It's a great point. Honestly, I didn't even think about, but it's I mean, that's just all the more reason why it takes more than a handful of organizations or people. Everybody has a different vested interest in how they approach, creating solutions. And, it's that, bringing all those perspectives to the table that really help. Oh, great. We got another question in the chat. Obviously, put your questions in the chat. We'd love to answer them. Anything is fair game. Questions about professional development, the paper we just talked about, just go ahead and hit us up with your questions. We're going to get into some questions. All right, so here's the question. Another question from Kofi McNair. If I mispronounce your name, I sincerely apologize. For future translation, could take advantage of optogenetics to stimulate plasticity, neurogenesis, like programming the stimulator. I guess what they're asking is like, do you foresee a future of like in vivo use of optogenetics, like using optogenetics in patients as opposed to just using it to study clinical models?
Yeah, that's a great question. So optogenetics, I think at least where we're at now, is probably going to be restricted to mice, where we can, do the genetic modifications, whether it's by actually changing their genetic material at the level of the genome, or by, giving viruses that can allow for basically viral mediated transmission of the gene into specific cell types. I don't think we're, at the point of really being able to modify the human genome in such a way that would make optogenetics possible. And
we probably could from a scientific perspective. I don't know from an ethical perspective if we really have the ability to do that properly. But I suppose we technically have, as scary as it sounds, we have the technology to probably edit a human genome if we really wanted to.
Yeah. Oh, yeah, for sure. I mean, when you look at things at the level of the embryo, right, you certainly could imagine a scenario where you modify the embryonic cells and then allow for production of a human from that. But you're right, the ethical implications are not consistent with where we are as a society. And I would probably be of the opinion that I hope we maybe don't get to that point. At least being able to edit the human genome at the at the level of the embryo. There is some potential.
They'll be like editing their own children's DNA before they're born, so that way
right.
Superstar athletes. All kinds of crazy stuff.
Exactly. You can imagine a scenario where, if you want to talk about equity too, the people who have the most money are able to, generate quote unquote perfect offspring, depending on
perfect is in the eye of the beholder, my friend.
Exactly. So yeah, it's a scary concept. I think with genetics and those things, there's a lot of ethical implications to be considered. Probably one of the most promising technologies from the genetic sphere is going to be things like CRISPR-Cas9, which I think it's probably out there in the public eye where people are at least aware that
Yeah, people
CRISPR
were.
is
I
a
mean, obviously,
thing.
CRISPR was right around the time I finished undergrad and was going
Mhm.
into medical school. All the news headlines about CRISPR were floating around. I mean, I assume that's. I mean, obviously, I don't follow that kind of stuff very closely. I assume most of that, those lawsuits and everything, have settled.
Oh, I'm not sure. I guess what was it that the claim to fame who actually
Yeah,
created
who
it was the
technically
issue?
invented CRISPR,
Yeah.
right? It was a Harvard group versus a Berkeley group or something like that.
Mhm.
And obviously they, collaborated heavily on the discovery, and then they were just fighting over who truly claims ownership. I mean, that's a very watered down explanation of the
Yeah.
lawsuit, but obviously that was the big news headline 5, 6, 7 years ago.
Yeah, I haven't really kept up with how that ended up going, but I'm sure it's somewhat settled or will
Yeah.
be.
But for anybody who doesn't know, CRISPR is basically relatively new. When I say relatively new, 10 years ago or so, probably now, discovery that pretty much allows scientists to just edit DNA at will. That's the simple explanation. It's obviously much more complicated in practice, but the simple explanation is we have the ability to just edit DNA. So, any other comments, Mike?
Yeah, so I think just on that, while I don't see optogenetics necessarily being, a way for translation in humans, I think, the point about maybe programming the stimulator in different ways is another way this research could progress. We understand that neurons have different firing patterns and frequencies, and we might be able to take advantage of that to modify the programming or the stimulator settings in order to, more specifically target that neuronal population by, essentially stimulating at the frequency by which they fire. So that might be a way to be a little bit more targeted in the therapeutic mechanism.
That's awesome. Well, on that note, I think it's a good time to kind of wrap things up. Thank you so much for being with us today, Mike. Everybody that joined the show, we hope that you really enjoyed the conversation. I think this was, obviously the first show we've done where we really honed in on a big scientific paper. I hope we've made it enjoyable for people who are not true scientists or clinicians, but are just fascinated by this kind of stuff. I hope we really made it enjoyable. Greetings out there to Neurosurgery TV. Welcome to the chat. We're just coming to the end of the hour here. But we hope that we've made this type of content really enjoyable for all of you. If you want to see more of it, please just let us know. Leave us a comment on the video. We're live every Tuesday and Thursday next week, starting at 7 p.m. So new live time next week, 7 p.m. Subscribe to the channel down below. If you really like the content, you want to support us as a nonprofit organization, you can join the community for $4.99 a month, or you can go ahead and head over to our website, brainandspinegroup.org/donate or neurosurgerytraining.org/donate, and you can leave a financial contribution. So that way we can continue to do this stuff. As a nonprofit organization, we love live streaming. We love creating educational content, but there's so much more that we do. And we're excited to share it all with you as we turn into the new year. We've got new initiatives for veterans, for patients to support that group of our community. We've got new research groups that, they've been in function. It's sort of been a little bit of an underground project that we're going to be putting out on our new website coming out hopefully early next year, that you can learn more about all the research that we do behind the scenes. So really, there's a lot to support. We're a nonprofit organization committed to creating tons of education, courses, live streams, resources out there for both young professionals, patients, enthusiasts, researchers, whoever you are. We're making content for you. All about aimed at improving brain and spine health. So thanks for being with us today. I appreciate all that you've done sticking around. It's great having an audience, and we'll see you next week Tuesday, 7 p.m. We'll see you then. We'll be joined by my co-host Josh next week, where we're going to take a little bit different approach to how we do the live streams that we hope you'll like. It's we're constantly evaluating how we approach things, how to make it as engaging and interesting as possible. And so we hope that next week's new time at 7 p.m., the new format will be just as interesting, if not more interesting and exciting for all of you. So have a great rest of your afternoon. Thank you for joining us on BSG Live, and we'll see you next